Every year, more than 100,000 people die from snake bites. A single vial of antivenom is made possible by the precise, orchestrated work inside venom extraction laboratories. Here, survival depends on layered safety systems, strict discipline, and split-second decisions, not luck. Behind these doors we ask, how exactly does deadly venom become medicine that saves lives? And who ensures no detail goes wrong? In rural hospitals across India, sub-Saharan Africa, and Southeast Asia, a child bitten by a cobra or a farmer stung by a scorpion faces a race against time. The World Health Organization estimates that over 100,000 people die each year from venomous bites and stings, most of them in places where antivenom is scarce or unaffordable. For every survivor, there are many more who suffer permanent injury or disability. The gulf between need and supply is not just a matter of logistics. It begins at the source, inside laboratories dedicated to transforming venom into medicine. Facilities like M-Toxins in Wisconsin operate with a clear mission: to provide the pure, traceable venom that underpins antivenom production for global health agencies and regional hospitals. Here, venom is not just a biological hazard, it is a raw material as essential as any vaccine component. Each batch, tracked by barcode and logged for decades, becomes the foundation for treatments that can reverse paralysis, stop internal bleeding, or save a child from cardiac arrest. Technicians, many of them university-trained, work behind locked doors and sterile barriers, aware that every drop they collect may one day decide the fate of a patient half a world away. The scale is staggering. A single laboratory session can yield enough scorpion venom for tens of thousands of vials, each representing a possible life saved. Yet the demand always outpaces supply, and the margin for error is razor thin. The stakes, measured in lives and futures, drive every protocol and every decision inside the lab. Inside the laboratory, order begins long before the first drop of venom is collected. Each animal, whether snake, scorpion, or spider, arrives in a sealed enclosure marked with a unique identifier. Technicians, following a strict checklist, use long forceps to transfer the animal from its home enclosure to a designated extraction vessel. Every movement is logged, including the species, the precise GPS coordinates of the animal's origin, the date, and the technician's identification number. This information is recorded both on paper and in a digital database, creating a permanent link between the animal, the sample, and the person responsible for each step. As animals are moved, their containers are scanned and barcoded, ensuring that even a single scorpion's venom can be traced back to its source years later. Traceability is maintained through an unbroken chain of custody. Each handoff, each extraction, and each storage event is entered into a metadata log. Venom samples are labeled with the same rigor. Every vial receives a code that matches the animal's record, the extraction date, and the technician's initials. These labels are more than administrative detail. They are the backbone of quality control, allowing labs to audit any batch for purity, origin, and handling history. Lot numbers and digital logs make it possible to track a sample through decades of storage, from the moment a snake is milked to the day its venom is shipped for antivenom production. This meticulous documentation is not optional. It protects against mix-ups, ensures compliance with international standards, and, most importantly, guarantees that every vial of antivenom rests on a foundation of verifiable data. Before a single animal is handled, technicians suit up in layers of personal protective. Nitrile gloves, lab coats, long pants, and closed-toe shoes form the base. Eye protection guards against accidental splashes, and for work with cryogenic storage or liquid nitrogen, heavy gloves are added. Each item is checked off a list, not just for compliance, but because even a minor lapse, a torn glove or a missing face shield, can turn a routine extraction into an emergency. The laboratory itself is engineered for containment and control. Airflow cabinets create invisible barriers, pulling airborne particles and aerosols away from the workspace. Stainless steel benches, sealed at the edges, prevent spills from seeping into cracks. Every surface is wiped down with RNase-free solutions to protect the integrity of both the venom and the data. Specialized tools, like venom cups and microcapillary tubes, are sterilized before each use and arranged in a precise order to minimize reaching or crossing hands during extraction. Training underpins every action. New technicians spend weeks shadowing experienced handlers, repeating protocols until each step is automatic. Every extraction begins with a verbal checklist, confirming personal protective equipment, verifying cabinet airflow, and double-checking animal identification. The process is slow by design. Rushing invites mistakes, like misaligning a snake's fangs over a collection vessel. If the fangs overshoot and touch the rim, the sample is discarded. Contamination is invisible, and its consequences ripple through the entire batch. In these moments, discipline and system redundancy prevent a single error from compromising months of work. The intersection of human vigilance and engineered safety is what keeps both people and product secure. A technician approaches a glass enclosure, eyes fixed on the patterned coils of a Bothrops pit viper. Every movement is measured. The snake is guided gently toward a parafilm-covered funnel, its fangs aligned with the membrane stretched across the opening. The parafilm acts as a barrier, soft enough to puncture, but strong enough to prevent splatter. With a practiced grip, the technician encourages the snake to bite down. Venom beads form on the underside of the membrane, collected into a sterile cup below. If the fangs overshoot and touch the rim, the entire sample is discarded. Contamination is invisible but consequential. For each snake, the interval between extractions is tracked in the database, never less than 4 weeks, allowing venom glands to regenerate fully. A few benches away, scorpion extraction unfolds with a different rhythm. The animal is held by the metasoma, its stinger poised above a microcapillary tube. Electrodes, precisely calibrated, deliver a low-voltage pulse, enough to trigger the release of venom without harming the animal. The technician watches for subtle cues, a twitch of the tail, the glisten of a droplet. Timing is everything. Overstimulation can stress the animal or dilute the venom. The extracted liquid is pipetted into a labeled vial, ready for immediate processing. Spider extraction demands even finer control. Some species are too small for manual restraint, so a brief exposure to carbon dioxide gently anesthetizes the animal. Microcapillary tubes, pulled thin over a flame, collect minuscule volumes, sometimes less than 1 microliter. Here, the technician's judgment is critical. Too much carbon dioxide, and the spider's recovery lags. Too little, and handling becomes dangerous. Each step is a negotiation between yield, purity, and the well-being of the animal. The tools and techniques shift with the biology, but the priority remains constant: precision over speed, safety over volume. A technician seals a freshly labeled vial, then places it into a refrigerated centrifuge. For 2 minutes, the machine spins at high speed, separating pure venom from trace amounts of blood or tissue. The resulting liquid is pipetted into sterile tubes, then frozen or transferred to a lyophilizer. This freeze-drying process transforms the venom into a stable powder, preserving its complex proteins and enzymes for years without degradation. Each lot is weighed, logged, and matched to its original barcode, ensuring that even decades later, a single milligram can be tracked back to the animal, the date, and the technician who performed the extraction. Before any venom leaves the lab, it undergoes rigorous assays. Technicians use mass spectrometry to identify protein composition and measure potency. Functional tests confirm the sample's ability to neutralize toxins or disrupt blood clotting. Only after these results meet strict standards does the venom move forward, destined for antivenom production or research pipelines. For antivenoms, the stabilized powder is shipped to pharmaceutical partners, where it is used to immunize host animals, typically horses. The animal's plasma, rich in antibodies, is then processed into antivenom that can save lives on distant continents. Some venoms take a different path. Decades ago, researchers discovered that a peptide from the Brazilian pit viper, Bothrops jararaca, could block a key enzyme in blood pressure regulation. The result was captopril, the world's first ACE inhibitor, now prescribed to millions for hypertension and heart failure. Each breakthrough, from antivenom to blood pressure drugs, begins with the same steps: careful extraction, stabilization, and validation inside the laboratory. Every year, demand for antivenoms rises as climate change shifts the range of venomous species and exposes new populations to risk. The next breakthrough in medicine, or the next life saved, relies on these invisible systems running without fail. Precision here isn't just science, it's survival. Share your thoughts below.